Jai Hind everyone. Today we are going to start the congestion control techniques. Here these are a few of the algorithms which we are going to discuss during this lecture. That is general principle of congestion control, congestion prevention policies, congestion control in the virtual circuit subnets we will be discussing. After that, congestion control in datagram subnets, load shedding and jitter control. So, we will start from the very basic question that arise into our mind. What is congestion? Right? Why congestion control is required and how the network is getting congested while during the communication. Fine. So, what is a congestion? We can see that is a state occurring in the network layer when the message traffic is so heavy that it slows down the network response time, right? Then we say this is the scenario, this is the situation where there is a congestion, right? What are the effects of congestion? The effects of congestion may include, as the delay increases, performance decreases, right? If delay increases, retransmission occurs, which creates the situation even worse, because already there is a heavy traffic on the network, and when retransmission of the packets occurs, it doubles the network traffic, right? So, it creates the situation worse even, right? With this diagram, we can see if here we take packets delivered, here the packets sent, at what rate the packets were sent and at what rate the packets were delivered. Here we can see this, that was the maximum carrying capacity of a subnet, right? Here we see that is a perfect. This one, it is okay, desirable, but when it is too much congested, there will be a decrease in performance, right? So, when too much traffic is offered, congestion sets in and performance degrades sharply. This is a situation of congestion in the network. So, now we'll see what are the various causes of congestion, why it is getting created. We say if suddenly multiple lines are there and the packets are arriving on each and every line for the same output line, right? All of a sudden packets arrive on 3-4 lines for the same output line where we have insufficient memory. So, okay, we say we can add on some memory, that will solve our problem. No, that doesn't solve our problem. Why it is so? Because more memory is also not a solution. Why it is so? Because suppose that was the memory, if I increase the size of the memory, say this one, larger the memory is, larger the capacity would be. If it is having larger capacity, that means it can buffer larger number of packets, right? Now, till the time these packets gets into the front of the queue, the time to live of that packet maybe that decreases and it will take a longer time to come at the front end or the front of the queue, right? That means again there will be a delay, right? So, we say increasing the memory is also not a solution. Okay, then what are the other causes? Fine, we may have the slow processors. The sender is a very fast sender, but the receivers are the slow receivers, or low bandwidth lines, It also causes the congestion to get created on the network, right? So we require some of the techniques to control that congestion. Fine. Congestion control, why we use it? To make sure that the subnet is able to carry the offered traffic. Fine. So that's why the congestion control techniques are required. So we'll see, here we have a general principle of congestion control. Number one, this is open loop. Open loop, okay, solved by a good design where it is being handled at the source side or destination side. What it includes? It includes when to accept new traffic, when it is going to allow new traffic to come, when to discard the packets and which packets needs to be discarded, right? When it will decide now the packets needs to be discarded, but it cannot discard any of the packet. That needs to be decided which packet to be discarded. It depends on the scenario, it depends on the situation, what kind of data we are working on. If it is a media file, for example, in that case, real-time data is more important than as far as your older data is concerned. But if we take the example of the text files, the messages, text messages and so, there the older one is much more important than the newer one, right? So it depends when to discard packets and which packet needs to be discarded. Making scheduling decisions at various points, wherever it senses that there is a congestion on the network, then we need to apply some scheduling algorithms, right? So it is required making scheduling decisions at various points. Second we have, that is a closed loop. First one, that was open loop. Second we have closed loop, which is based on the concept of feedback. Feedback could be explicit as well as implicit both, right? Here we have three parts. What are these parts? Number one, first of all, monitor the system, right? While we say monitoring a system, what does it mean? Detects when and where congestion occurs. It senses the channel, it senses the network, it detects when and where the congestion occurs, then pass information to where action can be taken, right? Where action can be taken, there it needs to pass the information, right? Okay, adjust system operation to correct the problem, right? So that is how the closed loop environment is working. Now we'll see what are the various congestion prevention policies at different layer. First of all, I start with the data link layer. Here we see we have retransmission policy, the out of order caching policy, the acknowledgement policy and flow control policy. Okay, then we move towards network layer. Here virtual circuit versus datagram inside the subnets, packet queuing and service policy, packet discard policy, which packet to discard and when to discard and so on, all the decisions related to discard of packets. Then routing algorithm, as we have already discussed in the previous lectures about the routing algorithms. Packet lifetime management, how to do that. Then, okay, now from the network layer we move towards transport layer. In the case of transport layer, there is a retransmission policy, out of order caching policy, acknowledgement policy, flow control policy and time out determination. These are few of the congestion prevention policies that could be implemented at different layers, like at the data link layer, network layer and the transport layer. Now we see the congestion control in the virtual circuit subnet. Firstly, we see the admission control. There will be agreement, right? And then route carefully so that we can remove the congestion, right? The first diagram, this diagram shows a congested subnet. There is a congestion, right? We can see here is a congestion, we can see here there is a congestion, right? So, in the second diagram here we have redrawn this subnet which eliminates the congestion and a virtual circuit from A to B, right? So, this is what a virtual circuit we can see in the diagram from source A to the destination B. Another method we have, that is a choke packets, right? What is a choke packet? That is some sort of a messenger, right, which informs the sender that the congestion has occurred and that needs to control its speed or a rate at which it is transmitting the packets, right. So, when the congestion occurs, a choke packet is sent back to the source to inform about congestion, number one. Then source reduces the traffic to the destination by X%, right, by some percent, say X%, right, ignores the following chokes in the fixed time interval. Then if again it is receiving a choke packet, that means still there is a congestion on the network. The congestion has not yet been resolved and still that exists in the network. So, if again choke packet, that means still congestion. That means it need to reduce its rate little bit more, reduces more. What reduces more? Rate at which it is transmitting the packets. Fine. If no choke packets again, that means congestion has been controlled and now it may increase its rate of transmission slowly, right. Okay, another method, hope by hope choke packets. In the previous method we have seen a choke packet was sent back to the source, right. Now, in the case of hope by hope choke packets, it will affect the every participating hope. What does it mean? A choke packet that affects only the source, and in the hope by hope we are having a choke packet that affects each hope it passes through. How it is doing that? This is the diagram, we can show that. In this diagram, diagram A, we see a choke packet has been sent to the source, that or the sender we can say, to reduce the flow, right. It has reduced the flow. If it is still getting a choke packet again, it will be indication for the sender to reduce some more speed or a rate we can say, right. But here in this case, that is hope by hope, when a choke packet has been introduced, it will inform each and every hope, each and every participating hope that a congestion has occurred. Try to decrease your transmission rate. Fine. And that is how we can see it is moving towards the sender and it has known that it needs to reduce the flow. After choke packets, we have load shedding. What is load shedding? When routers cannot handle packets, what is the solution in that case? Just throw them away. That is the only solution left, right? When we have the routers which are not able to handle the packets, then simply just throw them away. That is the solution we have, right? In a file transfer, an old packet is worth in a file transfer, let me repeat, an old packet is worth than a newer one. But if we consider the case of multimedia files, there we can see a new packet is much more important than the older one. That means we need to take a decision intelligently which packet needs to be discarded and when it can be discarded, right? So, intelligent discard policy is needed. So, there we can use the priority classes, right? Accordingly, that will be decided. So, we have jitter control. What is a jitter in the case of computer networks? When the packets are arriving, the rate of arrival of packets, if there is a variation, that means variation in the rate of arrival of the packets is known as a jitter. Too much variation is not acceptable, that is not required. So, we need to have some jitter control methods. So, we can see in this diagram that shows high jitter. High jitter, that means we can see minimum delay due to the speed of light, right? If we take the fraction of packets at this end and delay at this end, so we can see here this is the high jitter, right? Here it becomes very low, right? Packets ahead schedule are held, but the packets which are behind the schedule that needs to get out quickly, right? So, another algorithm, and which is a very important algorithm as well, we say, is a leaky bucket algorithm for the congestion control. What this algorithm says, as we have a bucket with a small hole in that, so the water drips out of the hole at a constant rate. No matter at what rate the water is getting filled in this bucket, how water drips out of the hole, that will be at a constant rate. So, the same concept has been applied in the communication network, right? Say here we see there is a host computer, right? We can have the multiple packets at a unregulated flow. The multiple packets are coming, but at an unregulated flow. Okay, now we are having a bucket which holds the packets, a bucket that holds packets, right? So, what is a bucket in the case of computer networks? That is the interface here we are having, which is containing some sort of container or a buffer, right, which is containing a leaky bucket, we can say. So, this bucket holds the multiple packets, whatever packets are coming, this bucket is holding, and at a regulated flow. Here the packets were coming at an unregulated flow, but here we see at a regulated flow the packets will move out of this leaky bucket, right? So, in this diagram A, we can see a leaky bucket with water. In the diagram B, leaky bucket with the packets, right? It is holding the packets. So, why we are using? For the traffic shaping, and it regulates the average rate. So, what the leaky bucket algorithm is? The leaky bucket algorithm discovers its use in the context of network traffic shaping or rate limiting, right? Also, a leaky bucket execution, and after this leaky bucket, I will be discussing about the token bucket algorithm. A token bucket execution are predominantly used for traffic shaping algorithms, right? This algorithm is used to control the rate at which the traffic is sent to the network and shape the burst traffic to a steady traffic stream, right? So, just to control the congestion and regulating the rate, we are using this leaky bucket algorithm. The disadvantages compared with the leaky bucket algorithm are inefficient use of available network resources, and the large area of network resources such as like bandwidth is not being used effectively, right. So, in short, what we can say, implementation is quite easy in the case of leaky bucket algorithm, as we have seen, that is of fixed size, a queue is maintained, right. On just a single click, a packet will be transmitted, and if we have a variable size, then byte counting leaky bucket with the counter n. Fine. On a click, a packet is transmitted if its size is less than n. If the size is not less than n, it is greater than n, that needs to be segmented, right. As I told you, after leaky bucket, we are having a token bucket algorithm. One of the disadvantage was there in the case of leaky bucket algorithm. The leaky bucket was holding the packets. Once there is an overflow of the packets, in that case, what is getting out? The packets were getting out. That means we are having a loss of information, loss of those packets, right. So, here we have a different concept, that instead of packets, now this bucket will be holding the tokens. Instead of packets, this bucket will be holding the packets, so that if there is an overflow in this bucket, then the tokens will be lost, not the packets. This is the main advantage over the leaky bucket of this token bucket algorithm. So, here we can see a host computer is there, one token is added to the bucket, say every delta t time, right. Now, the bucket holds tokens. Bucket holds tokens instead of packets, right. So, if there is a overflow, then these tokens will be discarded, not the packets, right. So, here we can see if the packets are coming on a unregulated flow, we can say the tokens are being stored in the bucket, right, and at a regulated flow that will be transmitted. So, it is more flexible, allows some more speed if burst error occurs. So, we will see one by one what are the steps and how it is working. The leaky bucket algorithm has a rigid output design at an average rate independent of the bursty traffic. In few of the examples, in few of the applications, when a large traffic or the large burst arrives, the output is allowed to speed up, and this calls for a more flexible algorithm. Preferably one that never loses information. Therefore, a token bucket algorithm finds its uses in the network traffic shaping or rate limiting, right. So, it is a control algorithm which indicates when traffic should be sent. This order comes based on the display of tokens in the bucket. Here in this case, in the case of token bucket algorithm, bucket contains tokens. Each of the token defines a packet of predetermined size, right. Each of the token defines a packet of predetermined size. Okay. The tokens in the bucket are deleted for the ability to share a packet. When tokens are shown, a flow to transmit traffic appears in the display of the tokens, right. If there is no token, that means no flow sends its packets. Hence, a flow transfers traffic up to its peak burst rate in good tokens in the bucket. right? So in short, we can say unlike leaky bucket, it allows some burstiness in the output stream, which gives a faster response to the sudden burst of inputs. When it is full, it throws away tokens, not the packets. So no packet loss. As I told you, this is the main advantage over the leaky bucket algorithm of token bucket algorithm. When it is full, what to throw, what to discard? It needs to discard the tokens. Packets are safe. So no packet loss, right? Implemented with a counter that counts the number of tokens. There is a counter. What that counter is doing? Counter is counting the tokens. On a click, a packet will be transmitted and the counter will be decremented, right? So, if we need to calculate the length of the maximum rate burst, we are having a formula C plus rho S is equal to m into S. So, we can find out the value of S as S is equal to C upon m minus rho. So, what is this C, m, rho, S and so on? So, if we need to calculate the burst length, so burst length could be denoted by S. The token bucket capacity could be denoted by C bytes, right? What is the token arrival rate? It is denoted by the rho bytes per second. Then what is the maximum output rate? It could be defined with the help of m byte per second. If an output burst contains a maximum of C plus rho S bytes, the number of bytes in a maximum, say speed burst of length S seconds in the ms. So, we can calculate with this formula, right? That is how we can calculate the length of the maximum rate burst, right? Let me discuss one of the important example that generally comes into the university question papers. That is, for example, a computer on a 6 Mbps network is regulated by a token bucket. The token bucket is filled at a rate of 1 Mbps. It is initially filled to capacity with 8 megabits. Now the question is, how long can the computer transmit at the full 6 Mbps rate, right? So here we can use this formula, S is equal to C upon m minus rho. Fine. So here the values are given and we simply need to put these values into the formula, right? So by substituting the values in this formula, we are already given the capacity as 8, and the value of m is 6, okay, and the transmit rate, right, and the value of rho is at 1 Mbps. So 8 upon 6 minus 1, or simply if we calculate, it is 1.6 seconds, right. So that is all about the congestion control techniques, and here I have included the references from where I have taken the contents in my slides. Thank you.